Welcome to Info Learning. Make sure to smash that like button and subscribe. Since the 1930s, astrophysicists have been trying to explain why the visible material in galaxies can't account for how galaxies are shaped, or how they behave. They believe a form of dark or invisible matter pervades our universe, but they still don't know what this dark matter might be. Dark matter is a mysterious substance thought to compose perhaps about 27% of the makeup of the universe. What is it? It's a bit easier to say what it isn't. It isn't ordinary atoms, the building blocks of our own bodies and all we see around us, because atoms make up only somewhere around 5% of the universe, according to a cosmological model called the Lambda Cold Dark Matter Model, aka the Lambda CDM model, or sometimes just the Standard Model. Dark matter isn't the same thing as dark energy, which makes up some 68% of the universe, according to the Standard Model. Dark matter is invisible, it doesn't emit, reflects, or absorb light or any type of electromagnetic radiation such as X-rays or radio waves. Thus, dark matter is undetectable directly, as all of our observations of the universe, apart from the detection of gravitational waves, involve capturing electromagnetic radiation in our telescopes. Yet dark matter does interact with ordinary matter. It exhibits measurable gravitational effects on large structures in the universe such as galaxies and galaxy clusters. Because of this, astronomers are able to make maps of the distribution of dark matter in the universe, even though they cannot see it directly. They do this by measuring the effect dark matter has on ordinary matter, through gravity. There is currently a huge international effort to identify the nature of dark matter. Bringing an armory of advanced technology to bear on the problem, astronomers have designed ever more complex and sensitive detectors to tease out the identity of this mysterious substance. Dark matter might consist of an as yet unidentified subatomic particle of a type completely different from what scientists call baryonic matter. That's just ordinary matter, the stuff we see all around us, which is made of ordinary atoms built of protons and neutrons. The list of candidate subatomic particles breaks down into a few groups. There are the WIMPs, weakly interacting massive particles, a class of particles thought to have been produced in the early universe. Astronomers believe that WIMPs might self-annihilate when colliding with each other, so they have searched the skies for telltale traces of events such as the release of neutrinos or gamma rays. So far, they've found nothing. In addition, although a theory called supersymmetry predicts the existence of particles with the same properties as WIMPs, repeated searches to find the particles directly have also found nothing, and experiments at the Large Hadron Collider to detect the expected presence of supersymmetry have completely failed to find it. Several different types of detectors have been used to detect WIMPs. The general idea is that very occasionally, a WIMP might collide with an ordinary atom and release a faint flash of light, which can be detected. The most sensitive detector built to date is Xenon 1T, which consists of a 10-meter cylinder containing 3.2 tons of liquid xenon, surrounded by photomultipliers to detect and amplify the incredibly faint flashes from these rare interactions. As of July 2019, when the detector was decommissioned to pave the way for a more sensitive instrument, the Xenont, no collisions between WIMPs and the xenon atoms had been seen. Although WIMPs have long been the favored candidate for dark matter, they're not the only candidates. The failure to find WIMPs, and the attendant frustration with not being able to account for a significant percentage of the universe's mass, has led many scientists to look at possible alternatives. At the moment, a hypothetical particle called the Axon is receiving much attention. As well as being a strong candidate for dark matter, the existence of Axons is also thought to provide the answers to a few other persistent questions in physics such as the strong CP problem. Astronomer Fritz Zwicky first predicted the existence of dark matter in the 1930s following his observations of the Coma galaxy cluster. The idea that there might be things in the universe that are invisible to us, that emit no light, has a long history going back hundreds of years to the days of Newton. With the discovery of so-called dark nebulae, clouds of interstellar dust blocking the light from background stars, and Pierre Laplace's 18th century speculations about objects which might swallow light, later to become known as black holes, astronomers came to accept the existence of a so-called dark universe. But in modern times, it was astronomer Fritz Zwicky, in the 1930s, who made the first observations of what we now call dark matter. His 1933 observations of the Coma cluster of galaxies seemed to indicate that it has a mass 500 times more than that previously calculated by Edwin Hubble. Furthermore, this extra mass seemed to be completely invisible. Although Zwicky's observations were initially met with much skepticism, they were later confirmed by other groups of astronomers. 30 years later, astronomer Vera Rubin provided a huge piece of evidence for the existence of dark matter. She discovered that the centers of galaxies rotate at the same speed as their extremities, whereas, of course, they should rotate faster. Think of a vinyl LP on a record deck, its center rotates faster than its edge. That's what logic dictates we should see in galaxies too. But we do not. The only way to explain this is if the whole galaxy is only the center of some much larger structure, as if it is only the label on the LP so to speak, causing the galaxy to have a consistent rotation speed from the center to edge. Vera Rubin, following Zwicky, postulated that the missing structure in galaxies is dark matter. Her ideas were met with much resistance from the astronomical community, but her observations have been confirmed and are seen today as pivotal proof of the existence of dark matter. In honor of this crucial and historic piece of detective work toward establishing the existence of dark matter, the revolutionary Large Synoptic Survey Telescope, currently under construction in Chile and scheduled to see first light next year, was recently renamed the Vera C. Rubin Observatory. Some astronomers have tried to negate the need for the existence of dark matter altogether by postulating something called modified Newtonian dynamics, MOND. The idea behind this is that gravity behaves differently over long distances to what it does locally, and this difference of behavior explains phenomena such as galaxy rotation curves which we attribute to dark matter. Although MOND has its supporters, while it can account for the rotation curve of an individual galaxy, current versions of MOND simply cannot account for the behavior and movement of matter in large structures such as galaxy clusters and, in its current form, is thought unable to completely account for the existence of dark matter. That is to say, gravity does behave in the same way at all scales of distance. Most versions of MOND, on the other hand, have two versions of gravity, the weaker one occurring in regions of low mass concentration such as in the outskirts of galaxies. However, it is not inconceivable that some new version of MOND in the future might yet account for dark matter. Although some astronomers believe we will establish the nature of the dark matter in the near future, the search so far has proved fruitless, and we know that the universe often springs surprises on us so that nothing can be taken for granted. The approach astronomers are taking is to eliminate those particles which cannot be dark matter, in the hope we will be left with the one which is. It remains to be seen if this approach is the correct one. Bottom line, dark matter makes up some 27% of the universe according to astronomical theories. It cannot be seen or detected directly via the existing tools of astronomers, but its effect can be measured via its gravitational pull on ordinary matter. Don't forget that humanity has came far and we would go farther than this. We have a lot more to learn about space and what it is holding. So I will leave you with that. Make sure to subscribe, like and comment what you want next.